Hi, this is Professor Stugard, and in this lecture, we're going to start discussing the concept of multiple integrals. And we're going to start with the simplest type of multiple integral, which is just a double integral over a rectangle. But before we get to the multiple integrals, let's make sure that we remember our integral notation way back from Calc 1 and what everything really stands for. So the first time we're introduced to integrals, we're told that there are method for calculating the area under a curve. And again, if I have a curve where my function is completely positive, as in the picture, on a interval from values a to b, to try to figure out what the area is going to be, we subdivide that interval into, well, subintervals, each of which have an equal width. And we use capital N subintervals. And when I take the length of my interval, which is b minus a, and divide it by the number of subintervals, capital N, I get delta x. And again, remember that triangle is really the delta. So again, that's the Greek letter delta, which represents our change. So again, that represents how much we change in the x direction with each rectangle we calculate. And then what we do is, well, if I want to approximate this area, I need to choose sample points inside each of those rectangles. And that's going to help me form my Riemann sum to approximate this area. And so the area, again, using our notation, is going to be the summation. So again, that Greek letter sigma, that's our summation, which means add up from 1 to n, which is our number of subintervals. And we're adding up f of x sub I, so again, evaluating x somewhere in that subinterval, and delta x. Well, that f, right, that's my height of the rectangle. And we can see in the picture that f of x sub I is my height of the rectangle. The width is my delta x. So again, it's just adding up the area of the rectangles, which, again, area of a rectangle is its height times its width. And so add up a bunch of rectangles. That's what this notation really is telling us to do. That's how we approximate the area under a curve. Now, if I want the exact area, well, I need infinity many rectangles. Well, infinity is not really a number. It's just a concept that means we want to grow without bound. But if I want to find the exact area and no longer an approximation, I'm going to take the limit as n goes to infinity of that summation. I want to use infinity many subintervals. And, well, that's kind of cumbersome, so we come up with a much better notation. Instead of saying the limit as n goes to infinity of my summations, we use kind of that little s, right? That integral notation that looks like an s, that stands for sum. And that is the genius of what really Leibniz brought to calculus. Technically, Newton did come up with it first, but if it wasn't for Leibniz developing this notation that we're using right now, it really would not be nearly as approachable to as many people. The genius of Leibniz really was in his notation and making this approachable for, well, anyone. And hopefully we can all kind of see that, when I look at those two different types of notation, well, that second one does look much, much neater, doesn't it? But the thing to remember is, of course, that integral notation really just means you're taking the limit of an infinite summation. And then obviously we make some changes with the other part. Since we're doing infinity many rectangles, well, I don't need x sub I anymore. I don't need to denote which subinterval I'm in because, well, I'm evaluating at every single point in that interval. Infinity many of them. I'm evaluating at every single one. And then the last genius of Leibniz notation was that we take that delta x and now it's a dx. So again, the delta x was your change in x. Dx is still your change in x, but when you take that change in x as it approaches 0, right, as that change becomes infinitesimally small, we use dx. And that's the same exact dx from our derivative, right? dy dx. That's the same notation. And again, there's the genius of Leibniz that allowed us to use that notation to do things like the chain rule and to treat them as fractions, even though they're not really fractions just yet. But that's really what our integral notation means. Now, the important thing to remember is that that integral notation didn't well, we use that to denote any sort of infinite summation. And you're going to see particularly when we get to chapter 16, we're doing vector calculus, which is, again, really we're doing a bunch of physics. Well, if I want to do infinite summations, I'm going to use that integral notation, and it is not going to have a single thing to do with area. It's just my way to write that I'm adding up infinity many things, and this is my nice, neat notation that does it. And again, that notation matters. When I have the integral of f of x dx, every single one of those pieces of my notation has meaning. And if you're a student who's gotten lazy or you like to work quickly and you don't necessarily write everything out, well, you're putting yourself at a huge disadvantage as we continue through with calculus, because again, it's not all going to be the integral of f of x dx anymore. It's going to be, well, other things, and they're each going to have very specific meanings, and they're all going to relate to things that are actually happening in physics, or even, abstract beyond our paper. But if you're not in the habit of writing your dx's and writing out your integrals with the proper notation, oh, you better start doing that now. Now, although again our integrals can be used for tons of different applications, we're going to start our double integrals and talking about our multiple integrals kind of in that same context. Instead of area, though, we're going to be talking about volume. We're going up one dimension, right? And so that also means that I'm not calculating just over an interval now, which was just my one variable x, right? From A to B on my x-axis. But now I need a region with two variables, or my R2 space, or some region in my xy plane. And so we're going to start with the simplest region we possibly can in my xy plane, which is, well, a rectangle. And so given a function of two variables that's always positive, if I want to try to calculate the volume over that rectangle and, well, under my surface, so again, we're talking about all of the region below the blue but above that peach color, we're going to denote our rectangle R in this manner. And so R equals, and then we have an interval for our x-axis, which is between A and B, and then an interval for our y-axis, which again we're going to denote as being between C and D. And so when we see that notation for R with those two intervals, again, that's just telling you the first interval is for your x variable, the second interval is for your y variable. Well, then, just like we did in Calc 1, what I want to do is subdivide my region, or subdivide my rectangle now into, well, subrectangles. And we use capital N subintervals for x, capital M subintervals for y. And again, that part does not matter as much because we're going to be taking infinite summations in just a minute. But what does matter is that each one of those subrectangles that we're looking down in the kind of that peach color, each one of those subrectangles is going to have an equal area in this case. And again, well, how do you find the area of a rectangle? It's, well, the length times the width. So the area of each of these little rectangles is going to be delta x times delta y. Again, the length times the width. And we're going to call that expression, delta x, delta y, our delta A. Well, then what we're going to do is we're going to choose a sample point in our small region to evaluate our function. Because, well, remember that function, when I evaluate my function of two variables, that's really my height. So that gives me my thin column, my rectangular box, my rectangular prism that now has a volume of its height times its base, right? Length times width times height. That's volume. And that's what we're doing right here, right? That the height is given by my function being evaluated at that point. And, well, my length and my width would be the delta x and the delta y, which combined together is really my delta A. Well, then what we need to do with this, though, is come up with an algorithmic process so that I can add up every single one of those subrectangles. And again, do it mathematically, right? Do it so that there's a pattern that we can follow. And so to do that, well, we're going to need a double summation because we're working in, well, two dimensions. But what this notation means is that first, I'm going to, well, move along basically one row and evaluate every variable of x, right, between a and b, do everything between a and b for just one value of y. And then once I've done that, well, then I'm going to move over and do that again for every value between a and b for x, but for my next value in y, and so on. I'm going to move down the entire thing. And again, that's what this notation means, is that algorithmic process for basically making sure we hit every single rectangle in our subdivided space. Now, just like with calculus 1, if I want to find the exact value, I need the limit as both m and n approach infinity. And then we're going to simplify with our integral notation. So again, what we're really doing is that kind of ugly expression right there. And then with our nice, neat notation, we can make it look way better. That limit and my two summations become just, well, two integrals. And then really the nice part here is that when we're writing out our multiple integrals, we typically just say, okay, it's over some region R, over some rectangle R, and I'm going to define R somewhere else because I don't want my notation to get ugly just yet. And then again, instead of evaluating at just sample points, we're evaluating at every single point in that entire region or in that entire rectangle. And as before, my deltas turn into d's to signify that we're taking infinitesimally small portions. Now, the most important theorem when it comes to calculating double integrals over rectangles, and we can apply this to, well, more general regions a little bit later, sort of, maybe, is that if my function is continuous on my rectangle, where again, x is going from a to b, y is going from c to d, what we're going to do to evaluate is use what's called iterated integrals. So iterated integrals just means that we have multiple integrals, in this case 2, and we're going to evaluate them starting from the inside out. Again, kind of like order of operations in PEMDAS, right? Always do the inside set of parentheses first. And so the nice part is my general notation, which is on the left. When I'm given that general notation, I can set up my integral in either way. I can either do it with respect to y first. And so again, if you look at the first one, dy, right, with respect to y. And look, my bounds c and d, those are my bounds for y. And we're going to have to do those first. And we need to make sure they match up. And then afterwards, well, after we do that, then we'll do it with respect to x. The dx is on the outside. And then from a to b. And again, those are, well, everything in terms of x. But we're going to do the inside part first. Do it with respect to y first, then x. But again, the nice part is, if I want to, I can swap them. As long as I'm being really careful about my notation and my bounds. The second example, well, I can certainly do it with respect to x first, which means my bounds need to be in terms of x. And then with respect to y second. And so those bounds would be on the outside. So let's do an example where we actually go through and let's verify Fubini's theorem, which means let's do it with respect to y, then x, and then we'll do it with then with respect to x and then y, and make sure we get the same results both ways. So again, this is a typical problem that we would see as we're doing multiple integrals. Right? We're integrating. We're taking the double integral over my rectangle R of 6xy squared dA, and I'm going to separately define what my region R is. So let's start with respect to y. All right, so if I do this with respect to y, just like when we did partial derivatives, this means that anything that has an x is really going to be a constant. So when I set this up, again, with respect to y first, so that means, again, dy, my bounds for y, which again is the second part of my interval, they go on the inside. And then anything else that's a constant, well, gets factored outside. And 6 and x, well, they're constants. My variable is y. So anything that's not a y is a constant, and we factor it out. Now, this is where, again, personal preference takes over. For me personally, once I get to this step, I would prefer to take this whole integral that I have in my parentheses, and I would actually like to evaluate that separately. I would prefer to do that on my scratch paper, do that entire integral out, and then bring my answer back over. But you certainly don't need to do that, and I'm not going to do that in this example. I'm going to keep that outside integral there the entire time, and just kind of go through and, well, we'll evaluate. But again, we're in Calc 3, so hopefully we know that the antiderivative of y squared is 1/3 y cubed. And again, we're going to evaluate that 1/3 y cubed at 2 and at 1 and find that difference. All right, so we have my expression. I got to evaluate now, but again, we can also make this a little bit easier on ourselves. One of the nice parts about leaving it in the problem where it is that, well, this 1/3 is a constant, and my 6x is still a constant. So I can combine those together and get 2x, which makes life a little bit easier. And then I'm just evaluating y cubed at 2 and 1. And 2 cubed gives me 8. 1 cubed gives me 1. Their difference is 7. 2x times 7 is 14x. And so now I have to take this integral with respect to x. The really important thing to notice here is that once I take my derivative with respect to y, my variable y needs to be gone. It better be gone at this point. If I just finished integrating with respect to y, I better not see any y's left over in my expression at all. But now, well, the antiderivative of 14x, again, should be just automatic for anyone in Calc 3. Obviously, that's going to be 7x squared. We're evaluating now between 3 and 4. So 4 squared is 16, 3 squared is 9. Their difference is 7. 7 times 7 is 49. And we just did this problem the first way and got a result of 49. And again, notice how this is a number, right? Just like when we do definite integrals in Calc 1, and my definite integrals where we have bounds gives me a numerical answer. It's the same idea here. We'll talk about indefinite integrals maybe a little bit later, but for now, we're going to be focusing almost solely on just definite integrals that have numerical solutions. But now I said the part of this example is I wanted to verify Fubini's theorem, which means I want to swap it around. I'm going to do it with respect to x first, and then with y. So it's the same idea, except, again, now x is my variable. So I'm doing it with respect to x. So the x's stay on the inside. I have my dx. My bounds are in terms of my x variable. And now my constants become my 6 and my y squared. So I can factor those out. And again, we could do this, by doing separate scrap work and bringing it back, but I'm going to leave everything together for this particular video so you can kind of see it. And I'm just going to work inside my parentheses first. Well, the antiderivative of x is obviously 1/2 x squared. And now we're evaluating that between 3 and 4. So there's my problem again. Now, just like before, well, here's a constant, 1/2. Here's a constant, 6y squared. I can combine those together so that I really get 3y squared as my constant in front. And then it's just a matter of evaluating between 4 squared and 3 squared. So again, 16 minus 9 is 7. And so 3y squared times 7 gives me 21y squared. And now I have just one integral left to take. And notice again that when I do my derivative with respect to x, after I evaluate my integral at its endpoints, my variable x is gone. My entire problem now is just in terms of y. And again, this should be a fairly simple antiderivative to take if you made it to Calc 3, because, well, raise the exponent by 1, which makes it y to the third, divide by 3. 21 divided by 3 is 7. So now I have 7y cubed evaluated between 1 and 2. 2 cubed is 8. 1 cubed is 1. Their difference is 7. 7 times 7 is 49. And, well, look at that. We got the same exact value both ways that we did it. And, well, yes, that's the point of the theorem, is that you can do it either way. And so a lot of times it might be smart to look at the problem first and figure out, well, what's the easier way going to be to do this? Just like we did with Clairaut's theorem, when we did partial derivatives, this is the same exact idea, the same exact type of theorem, just for integrals. Now, I almost hesitate to tell people this fact because students always use it incorrectly, but it is fairly valuable if you know how to use it the right way. If I have a function of two variables and I can factor into just a function of x and just y. So again, the key here is that I can factor. right? Factor means split it up as multiplication. If I can write it as a single function of x's times a single function of y's, again, by splitting up into multiplication, well, then I'm actually going to be able to split my problem up into two separate integrals. I'll be able to integrate with respect to x, then I'll be able to integrate with respect to y, two separate problems, and just bring their results back. So this last example, well, I can do that because I'm going to be able to factor my function. 6xy squared. It's all multiplication. Everything's being multiplied together. There's not a single plus sign in sight, which means I can absolutely factor it. And I'm going to factor it as 2x and 3y squared because, well, I know what I'm doing. And the fact that I can now set this up as two separate integrals. I can integrate 2x dx from 3 to 4, so on my interval for the x's, and I can integrate 3y squared dy on my interval for y, which is from 1 to 2. And the reason I picked this is because those antiderivatives are, well, pretty much trivial. It's x squared, and then evaluating from 3 to 4 gives me 7. Evaluating y cubed from 2 to 1 gives me 7. 7 times 7 is 49, and I get the same answer both ways. Now, again, I am cautioning you. If you're not 100% clear about this process, if you have any questions whatsoever if that function is factorable, don't use this fact. All right? Do it the long way. It's far, far better to take your time and get the answer wrong than it is to take your time and get the answer right than it is to try to get the wrong answer quickly, right? Don't try to get the wrong answer quickly. Get the right answer, take your time, and write it out. However, if you are very, very confident that you can factor your function, well, this trick can make your life a bit easier and make the problem go a little bit quicker too. All right. In our next lecture, we're going to be talking about how do I integrate over regions that are not just simple rectangles. What am I going to have to do there? But as always, give the homework a try, practice a little bit, and good luck.